Welcome to the second portion of chapter 10 that we were discussing three different aspects of traffic engineering, operation and control, speed, travel time, and delay study. In the first portion of this chapter, we have an introduction, what's the differences and what are the relationships between speed, time, and delay, and then we also covered the spot speed studies, and today we will be talking about the travel time studies as well as the intersection delay studies. So let's start with the travel times. So first question that has to come to our mind is, what do we need travel time studies for? First of all, we use it to identify problem locations on facilities by virtue of high travel times and or delay. So for any intersection, we may experience, or drivers may experience, longer times, lots of delay. So that would be a candidate location to do and obtain a travel time study. We also do a travel time study to measure arterial level of service based on average travel speeds and travel times. So travel time again is considered as a performance measure to identify the level of service for those arterial roads. We also do a travel time to provide necessary input to traffic assignment models, which eventually will focus on link travel time as a key determination of route selection. And we use travel time to provide travel time data for economic evaluation of transportation improvements. So if we are thinking of improving certain transportation facility, the travel time study will give us an indication, and the economic evaluation is this facility is a good economical facility that's going to boost the economy and help people getting in a fast and safe way. We also use the travel time study to develop time contour maps and other depictions of travel congestion in an area or a region. So, and we're going to show you an examples in the later slides. So, what are these techniques when it comes now to field study techniques related to travel time studies? The most common technique for conducting travel time studies would involve mainly on using a driving test cars through the study section. So we're gonna have the observer. So while the observer records elapsed time through the section and at a key intermediate points within the section. So we don't have to be at the intersection at a stationary location like what we used to do for volume studies or spot speed study. Now this is the first study that we mentioned that's gonna require having a driving test car, and the observer will be at the car to measure the elapsed time through that section. So the observer is equipped with a field sheet predefining the intermediate points for which travel times are desired. The observer also will be using a stopwatch, and that stopwatch is gonna be started when the test vehicle enters the study section. And now the observer will start recording the elapsed time at each intermediate point as well as at the end of the study section. So that's basically how we're gonna do the travel time study. So a second stopwatch. So the first stopwatch is gonna be used by the operator to measure the time once we get to the section, once we reach certain points at the intersection, and once we end the intersection, while a second stopwatch is going to be used to measure the length of mid-block and intersection stops. Their locations for those stops are going to be noted in the sheet that we're going to have to fill, and if the cause can be identified, it will be also noted why did we have to measure the time at this location in particular. So there are three different field study techniques that we can use while measuring travel time study, and the first one is floating car technique. And why we're talking about this, because we need now to be consistent. So to maintain some consistency of results, test car drivers, they have to be instructed to use one of those three different driving strategies. The first one is floating car technique. Floating car technique, that means the test car driver now is going to be asked to pass as many vehicles as pass the test car. So for example, if 4 cars pass the test car, the driver will be asked to speed up to pass the same number, which are the 4 cars. The second technique is the maximum car technique. So the maximum car technique, that means now the driver is asked to drive as fast, as safe, as practical as possible in the traffic stream without ever exceeding the design speed of the facility. So here we're gonna let the driver speed up and pass as many cars as possible within the speed limit associated to that facility. The third technique is the average car technique. The average car technique, now we're going to ask the driver to drive at the approximate average speed of the traffic stream, which is a bit different than number 2. Number 2 is the maximum. We're going to ask the driver, for example, if the speed limit is 55, we're going to ask the driver to drive at the speed limit. That means you can pass as many cars as possible, where the average car technique, now we're going to ask the driver to drive at the approximate average speed. The average speed can be a little bit less than the speed limit. If the speed limit is 55, but the majority of the cars are driving at 50 miles per hour, we are going to ask the driver of the test car to drive at 50 miles per hour. Or if it's 54, 55, again, it's all about the average speed of the entire traffic stream. This is here an example to show you a sample of a travel time field sheet. As you could see in this table, we have a 7-mile section of Lincoln Highway, which is a major suburban multi-lane highway. And as you could tell, we have different checkpoints. MP16, this means mile post number 16. MP17, that's mile post number 17. That means, if you could tell, from mile post 16 all the way to mile post 22, those are the 7-mile section. So as you can see here, this is second column. It shows the cumulative distance along the route. So by the time you reach mile 16, so 1 mile, 2 miles, 3 miles, all the way to by mile post 22, you have a total of 7 miles worth of length at that section. Then the third column shows the cumulative travel time. So by the time I reach mile post 16, I accumulated 1 minute and 35 seconds. By the time I reach mile post 17, I accumulated 3 minutes and 5 seconds, all the way until I reach mile post 22, where the observer at the test car measured 12 minutes to reach mile post number 22, all the way from the beginning of the test section. Now the next column would be the stopped delay. How much delay did we experience for each section? So for example, the first 2 mile posts, we did not experience any delays, while once we reached, now by the time we reached the mile post 18, we had 42.6 seconds delay. And this 42.6 seconds delay is related to how many stops. The car stopped 3 times, and here it shows you the section travel time. So they really traveled, this is the amount of travel time at that section, 2 minutes and 45 seconds. This is really per section, and that's why you could see it's per section. So that's 2 minutes and 45 seconds within that mile. And the last column is a special notes to show you a reason why did we have 3 stops and why did we have a 42.6 delays. Here it shows you that we had 3 stops, and those stops were due to the signal at mile post 17.2, 17.5, and mile post 18. Now we go to mile post 19. We have now again the cumulative distance. By the time we reach mile post 19 at 4 miles, the cumulative travel time is 7 minutes and 50 seconds. The stop delay for this section is 46 seconds. We had 4 stops, and the travel time for this mile was 2 minutes And now an explanation of that 46 seconds delay is stops due to signal at milepost 18.5 and double parked cars. If there is double parked cars, that means now the test car had to stop or at least slow down, and that also would cause some delay all the way to milepost number 22. So again, this is a discussion of the 7-mile section that we talked about. So we had checkpoints are defined in terms of mileposts. The elapsed stopwatch time was used to measure the time for each checkpoint. The section travel times are computed as the difference between the cumulative time and the successive checkpoints at that successive checkpoint. The segments ending in milepost 18 and 19, they displayed the highest amount of delay, as you recall, and therefore this represents the highest travel time. Something also that we noticed was double parking. That also was noted in one of the segments as a source of a significant amount of delay. This is here another example of travel time along an arterial. As you could tell here, we have the table of observation versus a graphical illustration of this travel time along this arterial. For example, let's take a look at the table. You could see here the travel time amount versus the number of observations. So for example, we saw 150, this is the travel time in seconds, 150 seconds and that was observed for one section. While for example 200 seconds, that was observed for 5 sections. So what you can do here to get the average travel time along this entire arterial is if you multiply t times n, which is the time travel in seconds, times the number of observations, and that gave us 219. If you divide this over 20 observations, if the t times n, the summation is 4,370. If you divide this by 20, which is the number of observation, is going to tell you that the average travel time per each one of these sections is 219 seconds. This is again a graphical observation of what we saw at that arterial. You could tell again one section had 150 seconds to go through that section. We also had one section that has 160. None of the sections had a travel time of 170 seconds, but look at this one here that goes well with what we saw on the table, where we had 200 seconds as the travel time was observed for 5 different sections. So that's the highest frequency, 5 observations at that travel time. Another way also to show the travel time studies and outcomes is by showing a travel time contour map. So as you can tell, this is here an example of that map. So travel time contour map, those are the travel time along all major routes entering or leaving a central area are measured. Then we come up with time contours that now we can plot them in their usual increment of 15 minutes. So as you could tell, here we have the first condensed contour line, which is 15 minutes, which is this one here. What does that mean? That means if you were travel along this area anywhere from one point to the other point, that you will be having roughly a travel time equal to 15 minutes. While now this second line of the contour travel time study, this is now 30 minutes. That means if you are within this area, you will be traveling roughly 30 minutes to your destination. Another way also of displaying travel time outcomes is the cumulative time along certain route. So as you could tell here, this is the x-axis is the distance from 0 all the way to 14,000 feet, and the y-axis, this is the elapsed time. And here we have two lines. So the dashed line is the theoretical line, assuming that there is no delays and assuming that you just went through from the beginning of the route all the way to 14,000 feet without any stopping, and that shows you roughly the average speed. And the slope of the line, of that line, is at any given segment is actually the speed. If you think about it, delta y over delta x, delta y is the elapsed time versus the distance, so time over distance, that's going to be the speed. Now, how about the continuous line? The continuous line, this shows you the actual performance. The dashed line, this is really the desired performance, while the continuous line, this is the actual performance with the delay. And that's why here you could tell at the beginning everything starts from 0, and then now once I see the continuous line and the gap between the continuous line and the dashed line, this is considered the amount of delay at that point. For example, once I stopped at this point, which has the highest delay, so at the distance 8,000 feet, this was the speed. If you want to measure the speed now, it's going to be delta y again over delta x, and now we had to stay at the distance 8,000 feet for that much of time. We had to stay from, this is here in minutes, we had to stay from roughly 2 minutes and 50 seconds all the way to 3 minutes and 40 or 3 minutes and 45 seconds. So this again, the length, this abrupt increase, or this increase here, shows you the amount of delay, because now the car stuck at that location for that amount of time, and now once the car start to move again, it catch up with the dashed line. That means again catch up now with the average speed one more time, and again you have some delay. Once the car starts to move again, it goes back to the dashed line, and so on and so forth. So this is again another way to represent the travel time and the associated amount of delay at every checkpoint. A third way of showing the travel time is the average travel speed versus distance. Here again you could see that the x-axis is AM northbound peak period speed versus the y-axis the average speed, and also in the second portion here, this is the PM northbound peak period speed profile versus the average speed. And now we're showing two examples. The first example here, this is with the presence of the HOV lane. As you could see here, we have HOV lane, we have before HOV, we have the mixed flow. So the continuous line, this is the mixed flow, and you could see that the speed would increase pretty significantly once now I introduce the HOV lane. So before the HOV lane, the speed was low. Now once I have the HOV lane, some of the traffic would go to the HOV lane, and definitely the speed of the HOV lane is way higher, because not much of vehicles would be using that lane. But still, HOV lane has a positive effect on the mixed flow, because now there's less cars from this point, and that's why the speed here is gonna be high. Same thing as you could tell here, but here again this is another condition where sometimes again with HOV lane here, this is the beginning and this is the end. The speed of the HOV lane is way higher than the mixed flow. So it happened to be here that once I start having the HOV lane, the speed dropped and it goes up again. So it can be either or. Now we move to another aspect in this chapter, which is the intersection delay studies. So there are several recommendations of the coming from the Highway Capacity Manual to measure delays at intersections using a minimum of 2 observers. Why? First, for unsaturated flow conditions with a maximum queue of 20 to 25 vehicles. Once now I start to see accumulation of vehicles, more than 20 or 25 vehicles, we have to have a minimum of 2 observers. Another recommendation of the HCM to measure delays at intersections using 2 observers, because it doesn't directly measure acceleration or deceleration delay, but uses an adjustment factor to estimate this component. Another recommendation was the method also uses an adjustment to correct for errors that are likely to occur in the sampling process. Remember, we're just doing sampling, we're not measuring every single car. Observers also must make an estimate of the free flow speed before beginning of a detailed survey. And that free flow speed can be done by driving a vehicle through the intersection during periods when the light is green and there is no cues, or by measuring approach speeds at a position where they are unaffected by the signal. So this is similar to when we talked about spot speed study. So before we do the delay study, we have to know what's our benchmark, what's the default free flow speed at this location, in order to compare it to what we're gonna observe at the intersection and be able to measure the amount of delay at that location. So looks like we have two observers. So now let's look into the tasks for these two observers. So the first observer number 1, need to keep track of the end of standing queues for each cycle by observing the last vehicle in each lane that stops due to the signal. The observer 1 will now start to count, and the count would need to include vehicles that arrive on green but stop or approach within 1 car length of queued vehicles that have not yet started to move. Observer 1 will do the measurements at intervals between 10 seconds to 20 seconds. The number of vehicles in queue are recorded on the field sheet. At the end of the survey period, the vehicles in queue counts continue until all vehicles that enter the queue during the survey period have exited the intersection. When it comes to observer number 2, during the entire study period, separate counts are maintained of vehicles arriving during the survey period and of vehicles that stop 1 or more times during the survey period. So that's very important. We need to know what are vehicles that they stopped once or more than once. The stopping vehicles also are counted only once. So that's the goal for observer number 2. We need to count the vehicles that enters through the study once, regardless of how many times they stopped. So now how are we going to connect what we measure from observer 2 and observer 1 together? So TQ, that's the average time in queue. TQ, that's the average time in queue, and it's measured as seconds per vehicle, and that can be calculated from what we measured and collected from observer 1 and 2. So TQ is equal to IS, which is the time interval between time in queue counts, times the summation of VIQ. VIQ, we get this from observer number 1, which is the sum of all vehicles in queue counts, and the units are vehicles, while VT, coming from observer number 2, this measures the total number of vehicles arriving during the study period, times 0.9, which is an empirical adjustment factor that we're going to be talking about it in a second. So this is here just a graphical or illustration of the table that we use for delay studies. Each column of the vehicle in queue counts is summed. The column sums and then added to yield the total vehicle in queue count for the study period, VIQ. So here we see the clock time, we see the cycle number, and now we see the number of vehicles in queue, how many were counted. So the question was the adjustment factor 0.9. Why do we need that factor? The adjustment factor 0.9 adjusts for errors that typically occur when this type of sampling technique is used. Such errors, based on different research studies, show that the results typically overestimate the delay. So how much delay we measure, we multiply that by 0.9 to reflect field conditions. Another further adjustment has to be done for acceleration and deceleration delay, that two values need to be computed. So the first one is VSLC. and that's the average number of vehicles stopping per lane per cycle. While the second number, or the second correction that we're going to be doing, is FVS, which is the proportion of vehicles arriving that actually stop. So VSLC can be computed as this ratio here: V stop, which is total count of stopping vehicles, over NC, the number of cycles included in the survey, times NL, which is the number of lanes in the survey lane group. While FVS, this is now V stop over VT. V stop, again, that's what we measured previously, which is the total count of stopping vehicles, over VT, and that's the total number of vehicles counted in the entire study. So another the adjustment factor now for acceleration deceleration. Once I get the free flow speed, once I get the VSLC, I'll be able to enter this table to get the adjustment factor for the acceleration / deceleration delay. So first of all, I need to know an estimate of the free flow speed, and that's why we said at the beginning of any delay study you need to know what's the estimated free flow speed. Once you get to know the free flow speed and you can calculate the VSLC, which are the vehicles stopping per lane, you should be able now to tell what's the adjustment factor to pick. The final estimate of the control delay is then computed as follows: D, this is D, this is the delay, total control delay, seconds per vehicle, is equal to TQ that we measured previously, plus FVS, which we measured in slide 32, times CF, which is the correction factor from this table right here, 10.6. So let's have an example to understand how can we measure the total amount of delay. First of all, this is the table, this is the sample data for a signalized intersection delay study, and as you could tell, we have the clock time from 5 p.m. all the way to 5:09 p.m. and we have 10 cycles during this time. So apparently that the cycle, which is the signal cycle, is 60 seconds. So we have 10 cycles, and as you see here, this is what we observe in the field. This is the number of vehicles in queue. If they stayed from 0 to 20 seconds, we had 4 vehicles, 20 seconds and more, 7 vehicles, 40 seconds and more, 5 vehicles. At 5:01 p.m., which is the second cycle, we saw 6 vehicles staying 0 and plus seconds, 0 to 20 seconds, or 0 to 19, and here 20 plus, which is 6 vehicles, and 5 vehicles stayed more than 40 seconds. So we keep doing this for the entire 10 cycles, which are about 10 minutes, and then we measure, we get the summation of all the number of vehicles in queue that they stayed 0 plus seconds, 20 plus seconds, and 40 plus seconds. And we can also, this can be now the summation of VQI, and VQI is the sum of all vehicle and queue counts. Now when it comes to VT now is which is 120. VT is the total number of vehicles arriving during the study period. The third number is V stop. V stop are 75. If you recall, V stop are the numbers of vehicles that they got to stop at the intersection. And finally, VFFS is 35 miles per hour. That is the free flow speed at that location. So once now I finish all these numbers, VQI, VT, VStop, and FFS, I'll be able to go to table 10.6, get the correction factor, which is CF, and calculate FVS from the previous slide plus the TQ in order to get the delay. And that's what we see here. So how can we get TQ? So TQ, as you recall, it's the IS, and that is 20. IS, this is the time interval between time and queue counts. So since we count vehicles every 20 seconds, or the delay every 20 seconds, 0 to 20, 20 to 40, 40 and plus. That's why this is the IS 20 times 132 over 120. 132, again, this is summation of all vehicles in Q counts, VIQ or VQI. This is the number of all the vehicles at the Q counts over 120. So, and that is VT, which is the total number of vehicles arriving during the study period. And that's why sometimes the number of vehicles arriving can be lower than VQI, which is the sum of all the vehicles in the Q counts, times 0.9, which is the correction factor. So this is first thing that we need to calculate towards getting to the D, delay. So first thing is TQ, which is 19.8 seconds per vehicle. Next, now we need to find the appropriate correction factor from table 10.6. So the number of vehicles stopping per lane per cycle is computed, which is VSLC, which is 75 over 10 times 2. What are these numbers? 75, this is the V stop, which is the total number of stopping vehicles, over 10 times 2. 10, this was NC, which is the number of cycles included in the survey, times NL, which is 2. This is the number of lanes in the survey lane group. So we had 2 lanes and we had 10 cycles. So, and the 75, again, this was the V stop, which were 75 vehicles. So once you get this ratio, you're gonna get, this is the number that we need to enter table 10.6, 3.75. Once you know 3.75, as well as the free flow speed, which is 35 miles per hour, you can go to the table and you will see that the correction factor is 5 seconds. So once you get that number, now you can calculate FVS. So as you recall, FVS is the ratio between V stop, which is 75 vehicles, over VT, total vehicles entering or arriving at the intersection, which is 120. So FVS, which is the fraction of the vehicle stopping, is 0.625. Once we get this, now we can arrive at the last equation, which is the delay, which is equal to 19.8, which is TQ, plus FVS, which is 0.625, times the correction factor that we got from table 10.6, which is 5. And now the delay can be measured or estimated equal to 19.8 plus 0.625 times 5. And now this is the delay per vehicle. Every vehicle will get delayed at this location of equal to 22.9 seconds. So with this, again, now in the summary, we finish chapter 10. We talked first about the spot speed study, then we moved to travel time study, and we ended this chapter with the intersection delay study. Thank you so much.